nuclear force. So two protons, actually to make you understand, so how to, suppose these are the two protons are there. The nuclear force, it's not like a Coulomb's law, like a line force, something and all. It will act along line joining the particles. So therefore, I'm just sticking on to we should not show anything like this. We should not show any lines. That one, they are interacting. This will be so. So some books what happen like they are shown. You should, but you should not draw a line. You should not draw a line and show this force. It will not act along line joining that particular thing. It's a totally wrong thing, that one. So that they will interact, and don't show that any lines of form. Just show that color. So that they are interacting here. Similarly, if there's a neutron and neutron, they will interact. Proton, neutron also will interact. So this everything is what happened is a nuclear force here. And we don't have till now the exact expression for nuclear force. Of course, we are able to use the properties of nucleus, but we are unable to generate the exact equation. It's still yet to be developed here. Only I think around 30% of that particular equation we are able to make it. We are unable to generate exact equation. So don't bother about the nuclear force equation. I think it's totally ruled out here. No. Okay, this nuclear force, what are the properties of this one? So first, we'll write the nuclear forces. It's a short range force. Means like when the distance between the nucleons is less than 10 to the power of minus 10 meter, no? Then of order 1 to like a 1 femtometer, then there will be the dominant, that one. Then next year, so whatever nuclear force, shall I put like this? Fn is almost some around nuclear force. This is nuclear force is some around 60 times. 60, some books they're called 80. 60 or 80, that one. See, nuclear force is 60 times greater than electromagnetic force. Now this will be a lot of confusion. So molecular force is electromagnetic force. Nuclear force is not electromagnetic. I think some books they have tried to further go it, but don't mess up things here. Because if you see the best foreign author books, they didn't say anything nuclear force here. But some of the books of Indian authors, no, they're trying to further say this nuclear force is nothing but the electrostatic force or that. They'll confuse you. See, like when Western science has not said anything, no, better let's not bother, because we don't do any research and say to conclude anything. No? Just follow the Western books, what they say. And let's not go beyond that one, because we don't have any practical data to analyze further. So it is of order 60 times greater than that of the, you can say, electromagnetic force. What is a molecular force? Molecular force is electromagnetic force, but the molecular force is not nuclear force. What is a nuclear force? Between the nucleons only. And where do this force is dominant only inside the nucleus? What about the nuclear force outside the nucleus? No, not there. Will not exist. Next, it is independent of charge. Electromagnetic force, you know, molecular force is electromagnetic at so many between molecules. No, independent of charge. This shall I put Fn? Better, I think it will be Fn is independent of charge here. Independent of charge, a best example is neutrons. No, these are the two neutrons. They are interacting. We know neutrons are neutral, but they are interacting. So therefore, the nuclear force is independent of charge. Next again, it is no, Fn is a not a central force. It's not a central force means the force of interaction between the two, between two protons, between two nucleons. Just it doesn't depends only on what? Only on the distance between the nucleons here. If it were central, I think, what do you mean by central? Example, Coulomb force is central force. So what do you mean by central? Suppose say plus Q1 minus Q2. The force of interaction depends upon the distance, no? It depends on distance. Whereas here what happened, the nuclear force is not a central force. And this is a central force here. This Coulomb force, central force. So the force of interaction depends on distance between the two charged particles. There's the Coulomb force. So we call that as the central force here. Whereas here nuclear force what happened, it just doesn't depend only on the distance between different. It also depends on what? The spin of nucleons. Fn what happened depends on, you can say like a B, C, D, this E. Fn depends on orbital and spin angular momentum of nucleons. What do you mean orbit? Yes, they'll have orbital angular momentum and spin. What about the spin? Spin about its own axis. So yeah, rough to make you understand. So I think, yeah, there are, do one thing. Yeah, let this be neutron. It will be orbiting this one, and it will have a spin about its own axis. So the angular momentum due to spin and also due to angular momentum due to its orbital angular momentum. The together that what happen will also determine the nuclear force. So not alone just the separation between them. If it were only depends on separation, I would have said central. This is beyond our limit. We have to purely enter into quantum mechanics, so nothing to do. But in exams can be asked. In matchings, they'll just put and they may test you. All these are information available in NCERT book or most of the for CBSE, no. So these are available in CIT books. It's available, so can be asked for you. Okay, agreed. So they're both some just only theoretical. So don't try to show that force. That's what you should do. Don't try to show any line here. What some books they're done, they're shown like this. Even that is also not permitted. So to have some imagination, I'm just showing some sort of color. There's the interaction between them. Okay, now when I go for the plot graph, nuclear force what happened next? A B C D E F, F is there. What is the nature of? Is it attractive or repulsive? Yes, it can be both. It can be attractive or repulsive. It all depends upon the distance between the nucleons. In SURMA, this curve is not there, but it's a very important. In SURMA, there is no much information about this curve, but it's a very important data. So it is. This is a 1 femtometer, 0.5, 1.5, 2, range in femtometer. This is a potential range in mega electron volt. No. Look at I'm interested in these 3 points. Look at this distance. Less than 1 femtometer. Then look at this and almost to look at these points. For distance between nucleons, so what is this range? Range means distance between the nucleons. So what do you mean by range here? Distance between nucleons. So when the distance between nucleons less than 1 femtometer, so what is the force? F equal to minus du by dr. The force will be what happened? Repulsive. Here. So then what happened? It will be where the slope is maximum here, no? Here slope is maximum, and you can check the force here and look at that as the distance increases almost for more than 2 or 2.5, almost the force happened will not exist. So shall we call it like a short range force, or almost at a distance of 8 femtometer? There won't be interaction between the nucleons. Almost at a distance more than 2 or 2.5, almost it has become very small value. So here we'll put it, the values here, let it be 0, minus 50, so they're short range forces. Just a distance of around 2 femto or 2 point, more than 2.5 femtometer almost will become 0. And at a distance of 8 femtometer, there's no interaction between the nucleons. Just imagine 18 to 10 to the power of minus 5. Distance between nucleons becomes 18 to 10 to the power of minus 5. There's no interaction. And that is what leads to like instability of atom. Why the some nucleus are not stable? This is what we can give reason. And it can be repulsive as well as attractive. Distance between nucleons less than 1 femtometer, almost you can say roughly here, around 0.7 or 0.8. And I'll further push it towards left, this one. Not up to the scale. So almost at a distance of, you can say like a 0.7 or 0.8, that one, the repulsive force, it becomes repulsive force. So nuclear force can be both attractive, repulsive. This like a, in where do what happen? If you go for supernova, there you can see that repulsive one. But what all our applications are related in this region only. What all the nucleus, what we study in chemistry or physics, no, whether distance between nucleons will be of this or will be of this kind. So in atomic structure, in periodic table, what we do see this or this one, we do see this. This is some like in supernova where there's no atomic structure. So or neutron star, they that we see. So that's why in books, often some books they just called only attractive. Nuclear force is attractive in nature. I think maybe it's talking in terms of periodic table. Nuclear force is attractive but some books they called it it's only attractive in nature. Maybe the author what happened is not bothered because in chemistry or physics what all we do applications we don't go for distance between nucleons because in nowhere in any nucleus where the distance between nucleons will be of this distance. So what all we measured is of this order. So then where do we see in neutron star, in supernova, getting this one, or when a nuclear fusion bomb, hydrogen bomb, there we see this particular thing. I don't think so. We have a syllabus anything neutron star or supernova or hydrogen bomb. So finally, what we are discussing only this part, and they say only nuclear force is attractive. I think justified, no? Keeping the syllabus in mind, maybe they might mention like this: nuclear force is attractive or repulsive nature depends on. We'll make a clarification. Depends on distance between nucleons or separation between nucleons. And let's not, I can't go for neutron star, all that one. Again, we have to go for black holes, everything from there we have to enter. Just leave that. Because when I plot a graph means, sir, where do we notice means I should give example. That's why I give example. So this is about the overall, the basic idea of the nuclear force. Now next question comes. Is it a conservative? I think we should not ask such questions, and nobody will ask you. Don't say anything conservative, non-conservative. But sir, you define potential energy. So these are the very some troublesome questions at this level. Maybe after 500,000 years, a physics teacher will be in a better position to explain this rather than now. We don't have much information regarding the basic equation. So still it's a debatable. Is it a conservative or non-conservative? To check with the conservative, non-conservative, what we should do? For that, we need a field idea, no? Nuclear field idea. I think we don't have much about the field, no? So I'll also leave this question mark. I think I don't have any ability of doing any practical research on these atoms regarding nucleus, everything that one. So still it's under debatable. So I'll leave that here only. I don't have, say like a, there's nothing called like any conclusion on conservative, non-conservative, because for that we need nuclear force, nuclear field. So force and field, nuclear field are not yet defined. We don't have any suitable equation. Only 30% we are able to generate. Fine. So this is about the nuclear force. Okay, next again. What can be the radius of the nucleus?